yeah, so as I said, it's not assessed. Just, hopefully this will be something that's useful to you. If it's not, then don't worry about it. I'm going to go over 4 things, and you got to think about it. We're trying to build up like the basic building blocks of maths. And the first is a set, just a group of objects, and then we define some rules over this set to make a group, and then we constrain that set even further to make a finite field. And then we apply finite fields to elliptic curves, which gives us a new group. And basically in cryptography, we're always doing operations on groups. Yeah, so it's kind of like, think about that mental model. We have these sets, and we apply operations to these sets, and it makes some rules, and there's less types of them. Yeah, so sets, it's basically a group of well-defined objects, and that can be anything. Literally, the set of all chairs in this room, the set of all students in this room, or the set of all numbers. Yeah. So, the elements of the set are just the objects inside it. Elements can be anything. And, basically we define these sets by some rules. And those rules can literally be anything, like the numbers less than 10. As long as there's a well-defined way to tell someone what's in this set, then that's the set. So, exactly, you can have the set of all colors in the rainbow. It's any group of objects can be defined by a set of any rules. So, what is a set? Can you define one? Anyone? No? Sure, you can think of one. No one's bothered. Right. The set is anything, like all the tables in this room, all the numbers, all the negative numbers. It doesn't matter. Yeah, and then we have this notation which helps us, at least in maths, write about sets in a precise manner. So, like, for example, x, the element x is within the set M. So, for example, 1 is in the set of numbers 0 to 10. But 11 is not in the set of numbers 0 to 10. And the reason I'm telling you this is just because sometimes, it depends how far you go, but you'll start reading this notation and it can be quite complicated or seem quite complicated, but really it's not that, once you can kind of just think back to what it actually is trying to say, rather than like looking at the complicated, potentially, notation, it becomes a little bit simpler, I think. Okay, and then in sets, there's this special kind of set, which is like the empty set, so the set of nothing, basically. And every set includes the empty set. So it's basically the set of no objects. And then we have some more notations, so like subsets, so you can have like the set A is inside the set B. Basically, it fits within every single element in the set A is contained within set B. So, like, for example, this set 2, 3, 4 is a subset of set 0 to 10, because 2, 3, and 4 both exist inside 0 to 10. Okay, and then these sets have this thing called order, and order is just the number of elements contained within inside this set. So the set of numbers 0 to 10 has 11 elements, so its order is 11. The empty set has 0 elements. Yeah, and these, like I was saying, these are just fundamental building blocks of maths. You can actually define most mathematical rules by starting from set theory and building upwards. And as you'll see later on in this lecture, we're going to show how we build up the rules of just addition, multiplication using sets. Yeah, and cryptography, we care about sets of integers. Why do we care about sets of integers? Anybody? Nobody wants to? You've got to help me out. Almost. I mean, it's because we're dealing with prime numbers, but specifically it's because we need to be precise. If we start going into decimal places, then we can't do calculations to a high degree of precision, which means we can't verify that something is true or not, or it's almost always going to be false. Yeah, so if we constrain these to whole numbers, then we know we're only going to get whole numbers. So 1 is always 1, it's not 1.01 or... Yeah, and then the other point is we care only about finite sets. So finite sets, what's a finite set? Can anyone imagine? Yeah, a set with well-defined order, so not infinite. And why is that important? Anyone imagine? Yeah, exactly. We want to constrain the amount of the calculation complexity of our cryptography by some value. Obviously, these values are very big, but if it's infinite, then the computation time is too large, and potentially these calculations aren't possible. Yeah, and then so there's this concept called modular n arithmetic, which I'm sure you've come across possibly. This is just a way of, in cryptography, how we can define sets, finite sets of whole positive numbers. Yeah, and what you have to think is actually it's just high school maths. So like, what's the remainder when we divide 200 by 11? That is the same as what is the modulus. What's 200 mod 11? Right, and I think if my math is right, it's 2. Yeah, and I don't know if people wanted to look at that, but you guys all come across modular n arithmetic before. Yeah. And I guess one thing to point out is, so like in mod n arithmetic, it's at least in addition. So if it's mod 11, there are 11 elements in that group, 0 to 10. So the order is 11 in that set. Yeah, and then this is just like, so you might see this sometimes, and it's just a fancy way of explaining it maybe more mathematically, and it can kind of look complicated, but you just have to think all you're doing is finding the remainder when you divide, this big number by this small number. And we don't care about how many times this number divides into the big number. We care about the remainder. Yeah, so I don't know if anybody wants to go through these, or if we're not playing ball, then we can just move on. Anyone? First one? 2. Next one? Yep. 6. I don't know why that says -1. That's just, imagine that's a question mark. Because it's not -1. -10 mod 11. Shouldn't say -1. So you have to think, when it goes negative, what we're still trying to do is we always want to move these values back within the set. And the set is 0 to 10. So it can only ever be a value between 0 and 10 if we're going mod 11. Right? So -10. How do we move -10 back to within the mod 11 set? It's 1. Yeah. Yeah, so we can just add 11 to it. Okay. 33 times 10 mod 11. It's a bit complicated, this one, maybe. I think I got this. So maybe it's a bit much. The answer is, well, we could do it if you want. 108. Good. Yeah, and then the last one is just another negative one. So 11 minus 24 mod 7. I think it's 1. So 11 minus 24 is 13. 13 plus 7 plus 7. So minus 13 plus 7 plus 7. I think it's 1. Let me see. I think I'll put the answers in, apart from that one. And that one's wrong. Yeah, so I mean, I was just rushing through this last night. But you get the picture. We're just trying to move it. Like, whenever you're looking at a mod or number, just think you're constraining this value within the set of integers mod 11, so, or mod whatever it is. And so actually you can think, okay, the number of answers it could actually be is just the n. So it could be 11 if it's mod 11, or 7. So you actually don't have that many possibilities. Yeah, and that's basically just a way of saying it. Mod n addition defines this set of numbers between 0 and n minus 1 with the order n. So the number of elements is n. Yeah, so here's another fancy way of like doing that notation. I guess that mod n should be 7, but you get the picture. Okay, so that's a set. A set is a group of numbers, at least in cryptography, at least to start with. We're thinking about a group of whole numbers between 0 and n. And then a group brings in this thing called an operation. So you all know what operations are, like addition, multiplication. So a group applies an operation to a set. And then through that, there's some more rules that have to be satisfied for it to meet the definition of a group. Yeah, and these rules are fancily called axioms sometimes. So you just have to imagine, like, not all sets are groups, but all groups are sets. Okay, and then this is kind of like the fancy way of defining it. And all you have to think here, in many ways, is this is like addition. So we define this group, say like mod 11. So the numbers 0 to 10. And we define the set is that 0 to 10, and the operation is addition. And then you check, does it satisfy these rules? So I think I've gone through, there's an example, right? So like, let's take this group 0 to 6. So does it have closure? And closure means, can I add this element A in the group to an element B in the group and always get an element within the same group? So, for example, 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is 5. 3 plus 3 is 6. 3 plus 4 is 0. 3 plus 5 is 1. 3 plus 6 is 2. Do you see what I mean? All these elements, there's nothing that I can add to 3 from the group that's not going to get me back into the group. Okay, then the next property that's interesting is the identity element, and that is, what can I add to any element in this group and not change that element? So typically in maths we use 0. Yeah. Oh, sorry, that was inverse. I thought I had some more stuff. Yeah. Yeah. So do we all get that? 0, or if it is multiplication, for example, the set is 1 to 6, what would be the identity element? You know, what if you're using this mathematical operation as multiplication, what can you times all elements by in the set 1 to 6 and always get the same element? So if I do 2 times 6, it's not going to get me 6. What? Yeah, exactly. So if I times 1 by all those elements, I'm always going to get, you know, that's the identity element. Basically, it just means it has no effect. Okay, and then we can use this identity element to think about the inverse. And the inverse is really important in cryptography, as we'll see later. But it's essentially, we have this element in the set, in the group A, and we want to find out what the inverse of it is. And that is, how can we apply some operation to this element to take it back to the identity element? So in addition, and what you have to understand is really subtraction in the context of groups doesn't, you know, we don't do subtraction, we just add but add can form a subtraction by defining the inverse. So that makes sense. So like, for example here, 6 plus 1 equals 7, which equals 0. 0 is the identity element. So the inverse of 6 is 1. I see some confused faces. I mean, feel free to ask some questions. Like, I'm not sure if I did this. So the inverse of 6 in the multiplication set, anybody? Try to work it out fast. It's quite an interesting one. So maybe a hard one. So you have to be thinking, what in this set can I times 6 by? That under mod n arithmetic, mod n multiplication is going to get me the identity element, which is 1. And it took me a while too. It's a little bit confusing maybe. Because you can also... Do we want to move on? I think I've got the answer here. I mean, so yeah, I mean, it's just, yeah, you can actually, so like 6 times 6 is 36. And 36 mod 7, so 36 divided by 7 is 5. 36 minus 5 is 1. Yeah, so maybe that wasn't a great example because it took me a while to realize you can actually just times them by themselves. But obviously, because 6 is an element in the group, you can times 6 by 6. Yeah, and as I was saying, so this inverse property is really useful in cryptography because when we have large groups, every element in the group needs to have an inverse. So that means we can always do one operation going forwards and then always remove that operation by applying the inverse. Yeah, okay, and then this last law, again, looks maybe complicated when you're looking at the notation, but actually this is just the rules that you all know from maths. So the associative law is basically saying if it's like 0 plus 5 plus 6 is the same as 0 plus 5 plus 6 with the brackets. It doesn't actually make a difference. Okay, and then there's a special property that some groups have, not all groups, called abelian groups, and that is commutativity. And that's basically saying it doesn't matter the order in which you do these operations, the order of which the set elements come. So like 4 plus 5 is the same as 5 plus 4. So again, like groups are these sets of objects. Then we take an operation. That operation can be anything that's well defined. What makes sense to us, at least initially, is we use addition and multiplication because they're operations that we all know. As you see later on, you can actually define different groups of different objects, different elements of the set, and different mathematical operations. And as long as those mathematical operations and those set of objects meet these criteria, these rules, then you've got a group. And if you've got a group, you know the group has these certain properties. So you can start, a lot of cryptography is based on the fact that these properties exist in groups. Yeah, and again, just to be thinking like, all you're actually doing is this is just maths. This is just like maths you did in probably high school. Addition, remainder stuff. And those rules are in many ways just a fancy way of stating them mathematically, what you know as addition. Okay, here's some more examples, I guess. Is this first one a set? Is a group, sorry. Is this set a group, 1 to 10, under mod 11 addition? And if not, why? So whenever you're looking at, is this a group, you've got to be thinking, what are the rules? Does it meet the criteria of all these rules? And if not, what rule is broken? Obviously. And if you can prove a rule, one of the rules is broken, then you know it's not a group. So is the set of numbers 1 to 10 a group under mod 11 addition? So we could go back to the rules. There's the rules as associativity, inverse, identity element. So this first one is not a group. It's not a group because it doesn't have 0 in. 0 is the identity element. Like if you're adding 1 to 2, there's no number in that set which you could add to any other number and not make a difference to that number. We need the identity element. The identity element is probably one of the easiest to check within a group because, it's at least under these conditions, it's 0, or in multiplication it can be 1. Does anyone want to have a go at the next one? Or are you giving up? Windy. I can just go through them. So this next set is not a group again. Anyone know why? So the set of numbers 1 to 7 under mod 9 addition. So it doesn't satisfy the property of closure because 1 plus 7 is 8, and 8's not in the group. And again, I wonder maybe an easy way to check that is, so mod 9 addition needs to have 9 elements in the set for it to form closure. The order of the set is 9. And here there's only 8. How about the set 1, 2, 3, 4 under mod 5 multiplication? What do you say? So this is a set, is a group rather. And it's because in multiplication we don't need the 0. The 0 doesn't make sense to model in multiplication. So the identity element here is 1. 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4. And I think if you go through, like 2 times 3 is 6, so it's 1. 2 times 4 is 8, so that's 3. You're basically checking that you can't create an element that's not already in that set. Okay, and then this one is a little bit more complicated, maybe too much so, but essentially here, so mod 14 multiplication. So I've actually defined it for you. And basically, what we're saying is which numbers less than 14, because mod 14 is going to create a set of numbers less than 14, but then we want to say which numbers can satisfy the group properties under multiplication. So obviously we need the identity element. The identity element is 1. Yep. And then we need to go through, what you can do manually is just go through all these elements, and you need to be thinking about, okay, which one of these has an inverse that is less than 14? So it's like, for example, 3 times 5 is 15, right? So 15 mod 14 is 1. So 3 is the inverse of 5. And the same for 9 times 11, I'd hope. And so the point is, all the other numbers, while they were in the set, they don't have inverses, so they're not in the group defined by this set. Makes sense? Roughly. You are just trying to, it is a bit complicated, but the reason I put this in, although I've not had time to actually add it into the presentation, is I really wanted to go through this and show you why RSA works. Because RSA is a set defined by 2 primes, P times Q. So it is this big set n, but actually the number of elements in the group is less than the set n. Is less than the number of elements in the bigger set n, because they're only the numbers that have an inverse. Maybe we'll save that for next year. Yeah, that's just the answers. Yeah, and really this is, we often term like Zn is really an important set, or even a group, mod n addition, because we'll see later. And then I guess the only other thing, this is where some maybe I've missed about or jumping a little bit too fast, but we have this concept of a generator in a group, and that is you can keep applying this this number, this generator, to itself to create every single other element within the group. So, for example, in mod n arithmetic, then it's 1 is the generator, because you can apply 1 plus 1 plus 1, and you're going to build every single element possible within that group, mod n. Because whenever you go past, whenever you get to n, you're going to go back to 0. Yeah, and so the reason this slide is kind of important, is maybe needs another slide on it, but is this fact that we have this isomorphism. And that's saying that actually these finite cyclic groups can be mapped to this simpler group, Zn, under mod n arithmetic. There is a mapping between every single element in this simpler set to this more complicated set. Yeah, and here's just another example of a generator. So when g equals 3 and you apply the operations, square power. Yeah, and you can see here, it's generating every single element in the group under multiplication, but it's different order. It's like 1 isn't, obviously 1 wouldn't be twice. I was just doing it all the way along. Okay, so now maybe it's going to get a little bit more complicated. And we define a field. So again, think about it. We just defined a group. A group is a constrained version of a set. Now we're going to constrain this group again into a field. Yeah, and a field is a set defined over 2 mathematical operations. You just got to think addition and multiplication. Right, is a basic 2 mathematical operations, right? And then again, we satisfy some certain axioms, some rules under which this set becomes a field with these 2 operations. Okay, so this is the complicated definition again. So first we have this set F. This set F needs to form an abelian group, so it has all those properties that we discussed: closure, identity, inverse, associativity, and commutativity. I think I have, we've just been through, those are the group rules. So the set F is forming this abelian group under addition, or under this operation. For now, it's addition, right? And under addition, the identity element is 0, it's called 0. Okay, and then this field also defines another group. So basically, this field is actually defining 2 groups. And that group is saying, okay, the initial set F that you gave me, let's take away the identity element 0, because it doesn't make sense under multiplication. And then that set, that new set, which is the old set minus the identity element 0, forms another abelian group with the identity element 1. So don't worry if there's too much, there's some examples coming. And then the other thing is this distributive law, which again is just something that you all know. That's maths, right? A plus B in brackets times C is the same as A times C plus B times C. Don't worry, I will share these slides as well, so don't. It's not. You done? Yeah, okay, so let's take it back to this set defined by Z7 or mod 7 over addition and multiplication. So two operations, two mathematical operations. Right, and the first law is it's got to form this abelian group under mod 7. And so that's all the numbers 0 to 6. Does it form an abelian group? And basically you can just check it, and the answer is yes, it does. Because you can satisfy all those properties. You know, so for example, commutativity, like 2 times 3 is the same as 2 plus 3 is the same as 3 plus 2. Closure, all the elements are in the set. Okay, and then so the next part is it forms an abelian group under multiplication if you remove 0, the identity element, the old identity element from the set. So under multiplication, it forms this new group which has 6 rather than 7 elements. Right? Because we had 7 elements and we took away 1. And basically, you're checking, does this new set of numbers form an abelian group under multiplication? And again, the answer is yes. Yeah, and then finally, again, it's just normal maths, at least for now, and it's, you know, do these operations satisfy this pattern, these rules? You know, it's like 1 plus 5 times 3 is the same as 1 times 3 plus 5 times 3. Right? You know, if I gave you that as like just a maths sum, you'd all be able to do it fine. And you'd understand they're the rules that you know. And we're just saying all the groups is trying to do is generalize what we mean by a mathematical operation so that we can potentially in the future make more complicated mathematical operations that still form groups. And again, we're only bothered about finite groups in cryptography. Everything needs to be finite so we can make calculations. Right. So then I'm just going to try to show you how this is then mapped to elliptic curves. So you've done a bit of elliptic curve cryptography. So maybe this will make sense. Hopefully it will. Yeah, and so the elliptic curve equation, y squared equals x squared plus ax plus b, is defining a set. You know, a set of coordinates, x, y coordinates, that will fit along this curve. Right? So for example, the point -1, you know, whatever that says, is in this set defined by the elliptic curve. Right? That's a set. You know, this line, anything on the line is in the set. Okay, but the problem is, if we want to use these for elliptic curve cryptography, that's not good enough, because there's a number of problems. So first, the set of all points on this curve are not all whole numbers. And as we discussed before, you have to have whole numbers if you want to do precise cryptography. Yeah, and again, this elliptic curve equation defines an infinite set. It goes on forever. So both those things mean there are some challenges when trying to use this set for cryptography. Fortunately, we can constrain the point values, so like the x and y coordinate space, over a finite field, such that x and y, all the values on the x-coordinate is a finite field from 0 to n, such that addition and multiplication meet these criteria that we just went through. And again, for y, is 0 to minus n minus 1 under this, under these two rules, addition and multiplication. I mean, it's a little bit, let me show you. And basically what that's doing is saying, okay, you can only be a point on this set if the equation, if when we're drawing this elliptic curve, it goes through a whole numbered positive x, y coordinates, right? Because we've already said, all these points on the elliptic curve that aren't whole numbers, we're just throwing them away. They don't exist. So then we get this nice set, right? This nice finite set of whole numbered x, y coordinates. And we can actually, those are just new elements to our set that are now finite, and we can start thinking about how we might convert that set into a group so we can do cryptographic protocols. Yeah, and as I said, so we've just shown how we can take an infinite set of any, decimal numbers as well, and constrain that into a finite set of whole numbers. But the problem is we want to turn it into a finite group. And again, the group has those certain laws that has to be satisfied. So we have to think, okay, what mathematical operation can we apply to this set such that we can satisfy the axioms, the rules of group theory? Yeah, so there's a number of questions that we have to answer. So first is, how do we add 2 points in this set together in a way that is going to create another point on the set, in the set. And then the other thing is, if I have a point A, how do I get the inverse of A? How do I take A away from itself so I can get 0? And then to that is, what is the identity element for this elliptic curve? We have to define those in a way that works for this set. And then once we can do that, if we can define all of those, if we can answer all those questions, then we have this thing called a finite abelian group, which we can then start running. The old protocols kind of, I think you can do RSA, you can definitely do Diffie-Hellman, and you can start building up much more complicated things, and it has some really nice properties. Okay, so yeah, I mean, this is kind of getting to the point where I sort of ran out of time. But elliptic curve point addition, you're saying, okay, how do I take P plus Q? How do I get a new point that's on the curve? Right, and so what you're doing is you're taking P and Q, we're finding the gradient of that line. And then we're setting the gradient of that line equal to the equation of the curve so that we can find the third point where that line crosses. And one of the really cool properties about elliptic curves is if you have 2 points on the curve and you draw a line, you're always going to get a third point. Except for some specific use cases. Okay, and then the only other special case is how do you double a point on the curve? What is P plus P? And for that use case, what is happening here is we're taking the tangent to the curve. So basically we're trying to find the gradient at that point, but the point doesn't have 2 points for us to calculate the gradient. We've got to calculate the tangent, which is like the exact gradient at that point in time. Yeah, and then again we draw this line. And so what this line actually gets us is this point which we call minus r. And we do this reflection over the axis. to get the actual point that is equal to p plus q. So I will be sharing some resources. I don't know how many people will be interested, but it's a lot more. It can be explained a lot better than probably I can in this resource, at least at the moment. But I just wanted to give you kind of a background, at least understanding or feel for what's going on under the hood in these curves. And you have to think, so we're doing an operation on a group, right? When we do p plus q, we're doing an operation on a group, but actually underlying all of this stuff, these are the x coordinates. These are operations on finite fields, which is why we can do s squared. Well, I'm not sure what s is, but do you see what I mean? So because the operations, when we go down to actually calculating, so the group operation requires us to do operations on the underlying finite fields, the x and y coordinates, which means we can do addition and multiplication. Whereas in the group, you only have one operation, addition. So let me just try reword that. So in the group that is defined by the elliptic curve, we only have addition. But in order to do addition in the elliptic curve, we have to be able to do addition and multiplication in the underlying coordinate space, the finite field. So I'm nearly done, to be honest. Okay, and then this one again is really cool and can be well explained with maths. I'm not clever enough at the moment to be able to do that, but I can share some resources which they basically explain how when we're looking at an elliptic curve, we're looking into 2D space. It's a 2D space, but if you project that 2D space into 3D, you can actually define why the identity element is what it is. But because that's complicated, for now we can just say that p plus minus p always goes through the identity element. And the identity element is a point on this curve. But actually, when you go look at it in 3D space, it's a whole line. And which is why, when I was going back to saying, if I take a line and I pass through another point on if I take a point on the curve and I go through another point on the curve, you can always get to a third point on the curve. So if I take p and I go through minus p, we get to the identity element. Yeah. Yeah, it's basically it. Yeah, and there's this thing called projective space, which it's complicated, but it's quite interesting. Yeah, and basically we include this identity element in this group for our elliptic curve group. Yeah, so this is just a sort of diagram that hopefully maybe explains it a little bit better. I'm not too sure if it does. I don't know if it's right. I just dropped this in this morning. Anyway, it's probably not that helpful. Oh, and then so the only other thing which I haven't included on here, but to think about is when we define elliptic curves for cryptography, we have this constraint, which is, what is it, Bill? It's like -4. There's a specific. The equation is y squared equals x cubed minus ax plus b. And then we have this equation which defines the constraints with which a and b can be. I can't remember exactly what it is. Should have it in here, but again, I kind of ran out of time. And the point is that we do that, we constrain these values because that constrains the shape that this curve can take. And if we break that constraint, then that means the fact that if I take one point on the curve and go through another point on the curve, I'm always going to get another point isn't true. Yeah, so again, like I think it just helps. This elliptic curve is complicated, but if you bring it back, all it's doing is defining a group that could be as simple as mod n arithmetic. And we define this operation, which is basically addition, but it's addition defined in this context. And the point is that this addition that we define over an elliptic curve meets these properties of the group. So p plus q is equal to q plus p. P plus q in brackets plus r is the same as p plus q plus r. Yeah, and then again, this identity element, it has no effect, right? P plus the identity element is p. Yeah, so I mean, I don't know how long I was, but that is me. It's not bad. So just on that, there's two things that it depends how keen you are and how much you want to dig into this. Because I'm really interested in this kind of stuff, and I found these two resources invaluable. So probably the bottom one is maybe, well, they're both really useful. The bottom one is more mathsy and very much, it's not about cryptography, it's about groups, group theory, finite fields. But it's if you like that notation and well-defined stuff, it's a good one to just try to get through because it defines all the rules properly. It has some proofs. It's a good resource. And then the second one, this top one, which I think is actually maybe better, particularly if you're a programmer, if you know Python quite well. Basically, this guy goes through, introduces elliptic curves, and slowly builds up these elements that I'm trying to rebuild up here. And you also develop them, you program them, so you can basically program your own elliptic curve. You define your own field, and it's quite cool. And he has a really good way of explaining a lot of the concepts that I've talked about here. So yeah, I mean, if anyone is going to do that, I'd be happy to help jump in if needed. Cool. Thanks.